Hello viewers, welcome to online course on Engineering Mathematics 3. Myself Sanjay Vishesh, Assistant Professor of Mathematics, Department of Applied Science and Humanities, Guru Nanak Institute of Technology. Here is the details of my contact information. Whenever you find any difficulties regarding my lecture or my course, you can contact personally or freely with my contact number here 877 576 364, or you can also send mail through my mail ID sanjay.vishesh@gnit.ac.in. So today we are going to discuss about so this is our third lecture. So the third lecture is basically on harmonic function and the Milne-Thomson method. Is the content of my lecture 3 of complex analysis. The first one is a Laplace equation on complex plane. Second, we are going to discuss about harmonic function and conjugate harmonic function of complex analysis. Then we'll study with some related problem on Laplace equation and the analytic function or harmonic functions. Then we are going to discuss about construction or analytic function. That means from this we are going to discuss about the Milne-Thomson method and some related problem on Milne-Thomson method. So here is the basic part or the content of my third lecture, Laplace equation, harmonic and conjugate harmonic function, and some problems on these two functions, that means Laplace equation and harmonic and conjugate harmonic function. Then we are going to discuss about the analytic function. So I have already discussed how to construct an analytic function. Okay, so here we are going to find analytic function. This is actually the different from the previous lecture I have mentioned in lecture 2 actually. So and then we are going to discuss about some related problem or on the Milne-Thomson method, and so from Milne-Thomson method we are going to find the analytic function and without finding u or without finding v. Okay, so let's start with Laplace equation. So what is Laplace equation? What is the definition of Laplace equation? So a partial differential equation of the form. So you know this is the partial differential equation del 2f del x square and del 2f del y square. This is actually the partial differential equation with respect to y, and this one is the partial differential equation with respect to y. And f is a function, is a complex function in a domain D. Okay. So the partial differentiation of the form del 2f del x square plus del 2f del y square is equal to 0 is called the Laplace equation. So we are going to study with the harmonic function. So harmonic function is basically a function f of x comma y which process continuous partial derivatives of first and second order and satisfied Laplace equation is called harmonic function. So we are going to study with the harmonic function. So harmonic function is basically satisfy the Laplace equation, and there are partial derivatives, first order and second order partial derivative are exist in a domain T on the complex plane. Then it is called a harmonic function. Okay, so this is the definition of harmonic function: a function f of x comma y which process continuous partial derivative of first and second order and satisfy the Laplace equation. That means del 2f del x square plus del 2f del y square is equal to 0. Then we will say this function is a harmonic function. So next we are going to discuss about the next definition is conjugate harmonic function. So conjugate harmonic is same as the harmonic function actually. So there is some slightly change on conjugate harmonic function. So if two harmonic functions u and v are the function of x comma y, satisfy the Cauchy-Riemann equation. So you know what is the Cauchy-Riemann equation? I have already mentioned, or I have already discussed in previous class. The two partial differentiation del u del x is equal to del v del y. So these two conditions are satisfied for the partial differentiation. That means del u del x is equal to del v del y, and del u del y is equal to minus del v del x. Okay, this is called a Cauchy-Riemann equation. So if two harmonic function u and v satisfy the Cauchy-Riemann equation, ux is equal to vy, that is del u del x is equal to del v del y, and del u del y is equal to minus del v del x, then they are called conjugate harmonic function. That means u is conjugate of v, or v is a function of conjugate of u. Okay. Okay, next we are going to discuss about some example of harmonic and conjugate harmonic function of complex analysis. So the first of here is the first problem. So the first problem is so that the function u is equal to cos x into cos hyperbolic y is harmonic, and find its conjugate harmonic. So basically the function u is harmonic, that means it satisfies the Laplace equation. So what is the Laplace equation? I have already discussed in the previous slide. So the equation is actually if u satisfied the equation del 2u del x square plus del 2u del y square is equal to 0, then we will say u is a harmonic function, and first order and second order partial derivative both are exist. So let's start with our solution. So here u is equal to cos x into cos hyperbolic y, this is given actually. So from this we will get the partial differentiation. So first of all we will get del u del x from this from the function u. So del u del x is equal to, you know, this is the partial differentiation with respect to y, x, where y is constant. So del u del x is equal to, so derivative of cos x is equal to minus sin x. So del u del x is equal to minus sin x into cos hyperbolic y, and the second differentiation with respect to x, and it will be minus cos x. So sin x, derivative of sin x is cos x. So the second differentiation with respect to x partially will get minus cos x into cos hyperbolic y. So similar thing will happen for the function u with respect to y. So if we differentiate it with respect to y, we will give it will give cos x into, and derivative of cos hyperbolic y is equal to, you know, sin hyperbolic y. As well, the second differentiation with respect to y partially will get cos x into cos hyperbolic y. So here cos x is actually the fixed value, and sin hyperbolic y, derivative of sin hyperbolic y is equal to cos hyperbolic y. So now we are going to find del 2u del x square plus del 2u del y square. What is the value of this term? So del 2u del x square plus del 2u del y square. So from this we will get the value is 0. So if del 2u del x square plus del 2u del y square is equal to 0, so from this we will say U is a harmonic function. This is the definition of harmonic function. Okay, so next we are looking for the conjugate harmonic function of U. So the conjugate harmonic, what is the definition of conjugate harmonic function? So if the function U is harmonic, that is it satisfies the Laplace equation as well as the Cauchy-Riemann equation is satisfied. So the conjugate harmonic function is of U is equals to V. So from this we are going to find the function V actually. So here V is actually the conjugate harmonic function of U, and if U is a harmonic function, that means any harmonic function is an analytic function. So if the function is an analytic, then this function satisfies the Cauchy-Riemann equation. I have mentioned in the second lecture already. So if the function is harmonic, this is actually the Cauchy-Riemann theorem actually, or Cauchy-Riemann condition. So if the function is analytic, then the Cauchy-Riemann equation are satisfied. So here let V be the conjugate harmonic of U, So del U del X is equal to, and satisfy this equation. Okay, so del U del X is equal to del V del Y, and del U del Y is equal to minus del V del X. So from this we are going to find the function V, and V is actually the conjugate harmonic of U. So okay, now we will put the total differentiation dV, and dV is equal to del V del X into dx plus del V del Y is equal to dy. This is actually the total differentiation of the function V, and V is equal to function of x comma y. So from this we'll so now applying the Cauchy-Riemann equation. So del V del X is equal to del V del X is equal to minus del U del Y, and del U del Y and del V del Y, and this is equals to del U del X. Okay, so from the first equation, that is the total differentiation, we will get dV, and dV is equal to minus del U del Y into dx plus del U del X into dy. And the value of del U del Y, so I have already find this partial differentiation. So the partial differentiation, okay, look at the previous slide. I have already find this one. So del U del X is equal to minus sin x cos hyperbolic y, and del U del Y is equal to cos x sin hyperbolic y. Now if we put these two values in this expression, we'll get this one. Okay, so dV is equal to minus cos x sin hyperbolic y into dx minus cos x cos hyperbolic y into dy. So this expression can be written as a d operator, so minus d of sin x into sin hyperbolic y. So derivative of sin x sin hyperbolic y is actually this one, minus of this. Okay, so now integrating on both sides with we will get b is equal to minus sin x sin hyperbolic y plus c, and c is the arbitrary constant. This is a real constant. Okay, so this is the conjugate of the function u. I think this is a very interesting example on complex function. So there is a u is given, so from this we will find the function v. Okay, next we are going to discuss one more example on harmonic and conjugate harmonic function. So here is the example. So if f of z is analytic, so f of z is analytic, that means fz is satisfy the Cauchy-Riemann equation as well as it satisfies the Laplace equation, or f of z is harmonic function. Okay, so if f of z is harmonic, then we will say u is harmonic function as well as V is harmonic function. So if U is harmonic, then U satisfy the Laplace equation, that is del 2U del x square plus del 2U del y square is equal to 0, as well as V is harmonic function, that means del 2V del x square plus del 2V del y square is equal to 0. Okay, so then prove that del 2 del x square plus del 2 del y square of mod of f dash z, and f dash z is equal to derivative of f of z equals to 4 into modulus of f dash z whole square. Okay, so let's start. So here f of z is equal to u plus I. So f of z be any function, and f of z is equal to u, and u is a function of x comma y, and v is a function of x comma y as well. So the first derivative of this function is f dash z. So f dash z is equal to, with respect to x, so we'll get ux plus I into v of x. So ux is the partial differentiation with respect to x, and vx is also the partial differentiation with respect to x. So from this we'll get the modulus value of f dash z as well as f of z. So the modulus value of f of z, you know, mod of f of z is equal to root over of u square plus v square, as well mod of f dash z is equal to ux square plus vx square root over of. This is the modulus value of a complex number. So you know the modulus value of a complex number z is equal to root over of x square plus y square as well. So that is f dash z, f of z whole square. So from this we'll get f of z whole square is equal to root over of x square plus y square whole square, that means u square plus v square. And as well f dash z whole square is equal to root over of ux square plus vx square whole square, that is ux square plus vx square. Okay, so from this we'll get the modulus value of f of z and f dash z. So now we are looking for the partial differentiation of ux, u and v. So what is the partial differentiation of u square? So here is the partial differentiation of u square. So del x of u square is equal to 2u ux, and the second differentiation with respect to x, this is not a y actually. So the first differentiation with respect to x partially, it will be 2u ux, and the second differentiation with respect to x of u square is equal to 2 into u double x, and u double x is the second differentiation with respect to x plus ux square. Okay, so similarly we'll get the second differentiation with respect to y of u square, and it will be 2 into u y, and u y is equal to partial differentiation with respect to y plus uy square. Okay, so from these two equations we are actually looking for the harmonic function of u. So what is the harmonic function is, you know, so if the second differentiation with respect to x and with respect to y for u square, and it will be 2u uxx plus uyy. If we common 2u from these two equations, we'll get uxx plus uyy plus 2 into ux square plus uy square. Okay, so this is actually the harmonic function, you know. So f of z, I have already told you f of z is analytic, that means u and v both are harmonic function. Okay, so that's why uxx plus uyy is equal to 0. So from this we'll get 0 plus 2 into ux square plus uy square, where u is a harmonic function. Therefore the second order differentiation del 2 del x square plus del 2 del y square of x square, and it will give 2 into ux square plus uy square. Okay, so similar thing will happen for the function v square. So del 2 del x square plus del 2 del y square of v square, and it will be also 2 into vx square plus vy square. Okay, so actually my problem is uh, we actually prove that del 2 del x square plus del 2 del y square into f dash z is equal to this. Okay, where f dash z is equal to ux square plus uy square, and f of z is equal to u square plus v square. Okay, so next one. So therefore, okay, I will take the left side of the given problem. Del 2 del x square plus del 2 del y square of mod of f dash z. Okay, so here f dash z is equal to u square plus v square. Okay, so del 2 del x square plus del 2 del y square of u square is equal to, this is the value of this u square, second derivative of u square, 2 into x square plus uy square, and del 2 del x square plus del 2 del y square of v square. So if we separate this function, first one is second derivative of u square, and second part is second derivative of v square, we will get this ux square plus uy square, and from second differentiation we will get vx square plus vy square into 2. From this it will give, okay, from this it will give 4 into ux square plus vx square by using the CR equation. So here this is actually the CR equation, ux is equal to vy and uy is equal to minus vx. So applying the CR equation we will get 4 into ux square plus vx square. So ux square plus vx square is, this is the f dash z, the modulus value of f dash z, so that is 4 into f dash z whole square. So hence proved. We will continue our discussion on lecture 3, harmonic function, conjugate harmonic function, and Milne-Thomson method. Before we start the Milne-Thomson method, I will say something. If the function f of z is analytic in the complex plane, then u and v both are harmonic function, or both are analytic function. But the converse part is not true. That is, if u is harmonic function or v is harmonic function separately, then from this we cannot be say as necessarily f of z is analytic. But by the Milne-Thomson method, we have seen that f of z is analytic function and u and v are the conjugate harmonic function. That means u and v both are satisfied the Cauchy-Riemann equation. If one of these, say u, is given, then determine f of z directly without finding v is due to Milne-Thomson method. So basically Milne-Thomson method is a very interesting and very useful method for finding the analytic function or finding the function f of z. So if there is a function u is given but v is not here or v is not given, then from this we will directly find the function f of z without applying or without finding v. Similarly, when v is given, so from this we will directly find f of z without finding u. So here is the proof of the theorem basically. So let z is equal to x plus iy. This is this is the complex point, variable point, and therefore z bar is equal to x minus iy. So z bar is equal to, this is the conjugate of z, and z bar is equal to x minus iy. So from this we'll get, from this two equation we'll get x and y. So if we cancel y from this two, we'll get x, and the value of x is equal to 1 by 2 into z plus z bar, and the value of y is equal to 1 by 2 into z minus z bar. Okay, so these are the value of x and y with respect to z and z bar. Okay, now we are looking for find the function f of z, and f of z is equal to u of x comma y plus I into b of x comma y, and if we put x is equal to this and y is equal to this, so we will get the value with respect to z and z bar. So f of z is equal to u of x z plus z bar by 2 comma z minus z bar by 2 I, as well I into b of z plus z bar by 2 comma z minus z bar by 2I. So now we put z is equal to z bar, that means y is equal to 0 and x is equal to z, so that f of z is equal to u of z comma 0 plus I into b of z comma 0. Okay, now we are going to find the first derivative of f of z. So f of z is equal to derivative of f of z is equal to f dash z, and this is equals to del u del x plus I into del v del x. So applying the CR equation, and it will change, and it will give del u del x minus I into del u del v. CR equation of complex function. So now we will choose del u del x is equal to phi 1 of x comma y, and del u del y is equal to phi 2 of x comma y. So del u del x and del u del y are both are the continuous function, and both are function of x comma y. So that's why I will choose del u del x is equal to phi 1 and del u del y is equal to phi. Okay, now we put phi 1 x comma y and phi 2 x comma y in the place of del u del x and del u del y. Then the first differentiation f dash z will be changed, and it will be phi 1 x comma y minus I into phi 2 x comma y. Okay, so from this if we put x is equal to z and y is equal to 0, this is actually the proof of the Milne Thomson method. So f dash z is equal to phi 1 z comma 0 minus I into phi 2 z comma 0, where x is equal to z and y is equal to 0. Same. So now integrating this, we get f of z is equal to integration of phi 1 z comma 0 minus I into phi 2 z comma 0 dz plus c, where c is an arbitrary constant. That is, from Milne Thomson method we can find f of z without finding v. That is, f of z is equal to phi 1 z comma 0 minus I into phi 2 z comma 0 dz plus c. This is the function of f of z. Okay, where phi 1 and phi 2 are the given functions. So phi 1 is equal to del u del x and phi 2 is equal to del u del y. So phi 1 and phi 2 are the two partial differentiation with respect to x of the function u. Okay, where c is the arbitrary constant. We are going to find f of z without finding u. Okay, so here is the expression of the function f of z. This is actually similar as the first one. So if we put del v del x, del v del y is equal to psi 1 of x comma y, and del v del x is equal to psi 2 of x comma y. So we will get the function f of z, and f of z is equal to integration of psi 1 z comma 0 minus I into psi 2 z comma 0 into dz plus c, where c is an arbitrary constant, Okay, next we are going to talk about some related problems on Milne Thomson method. So the first problem is actually the proof that u, so u is given, u is equal to x to the power 3 minus 3xy plus 3x square minus plus 3x square minus 3y square plus 1 is a harmonic function. Next we are going to find the analytic function u plus iv, that is f of z, without finding the function v. So u is equal to xq minus 3xy plus 3x square minus 3y square plus 1. If del 2 del x square plus del 2 del y square is equal to 0, then we will say this function is a harmonic function. So here u is equal to this, so from this we are going to find the first order partial differentiation with respect to x, and then we are going to find the second order differentiation with respect to x. So the first order differentiation with respect to x, and it will be 3x square minus 3y plus 6x, where y is constant, so 3y square plus 1 is 0 with respect to x. And del 2u del x square is equal to, so derivative of 3x square is equal to 6x, and 6x is equal to 6. So the second order differentiation with respect to x is equal to 6x plus 6. And similarly we are going to find the derivative for the function u with respect to y. So first of all we are going to find del u del x. So del u del x is equal to minus 6xy minus 6y, where x is a constant term. Okay, so this is actually the partial differentiation. So from this we are going to find the second order differentiation, and it will be minus 6x minus 6. So therefore the second order differentiation with respect to y and second order differentiation with respect to x, or 2x del 2u del x square plus del 2 del y square, and it will be, okay, after cancelling the term 6x minus 6, we'll get this is actually 0. So this is actually the Laplace equation, you know. So the second order and first order partial differentiation are exist as well. The function u satisfy the Laplace equation. So from this we will say this function, that is u, is a harmonic function. So next we are going to find the analytic function without finding v. So how? So if we apply the Milne-Thomson method, we can find the analytic function without finding the conjugate of u actually. So here, so if the function is analytic and satisfy the Cauchy-Riemann equation, then from this we have to find the analytic function f of z without finding v. And similar thing will happen when v is analytic and satisfy the Cauchy-Riemann equation. Then from this we have to find f of z without finding u. Okay, this is the Cauchy-Riemann Milne-Thomson method. So here u is given and u is also the harmonic function, so that means u is an analytic function, and u is satisfied the Cauchy-Riemann equation. So what is the Milne-Thomson method when u is given? So this is the expression of Milne-Thomson method. So f of z is f dash z is equal to phi 1 z comma 0 minus I into phi 2 z comma 0. So I have already mentioned in the previous slide, this is the expression of f dash z, or that is f of z is equal to integration of phi 1 z comma 0 minus I into phi 2 z comma 0. So here del u del x is equal to phi 1 of x comma y, and del u del y is equal to phi 2 of x comma y. Okay, so phi 1 of x comma y is basically is partial differentiation first order with respect to x, and it will be 3x square minus 3y square plus 6x, and phi 2 of x comma y, and this is actually the partial differentiation of u with respect to y, and it will give minus 6xy minus 6y. Okay, so at x is equal to z and y is equal to 0, phi 1 of a z comma 0 is equals to 3z squared. Okay, y is 0, those are second term is 0, and the third term is 6z. that is phi 1 of z comma 0 is equal to 3z square plus 6z. And similarly, when we put x is equal to z and y is equal to 0 in the second expression, we'll get phi 2, the value of phi 2, at x is equal to z and y is equal to 0, we'll get minus 6 into z into 0, that is the first term is 0 as well, the second term is 0. So f dash z is equal to and the value of f dash z and is equals to 3z square plus 6z minus I into 0. Okay, so now integrating we get integrating on both sides, we get f of z is equal to, so integration of 3z square is equal to z cube, integration of 6z is equal to 3z square plus c, where c is an arbitrary constant. Okay, next we are going to talk about the second problem. Next we are going for we are looking for the second problem. If a function, analytic function f of z, find the analytic function. We will go for the second problem of Milne-Thomson method. Find the analytic function f of z is equal to u plus iv, of which the imaginary part b is equal to e to the power x into sin y. So here the function that is the imaginary part b is given. So from this we are looking for find the analytic function f of z without finding u. So that means we are going to that means we'll apply the Milne-Thomson method for finding the analytic functions. So here b is given, and so u is not given in this problem. So b is equal to e to the power x into sin y. So if b is given, then what is the Milne-Thomson method? The Milne-Thomson method is actually f dash z is equal to psi 1 z comma 0 plus I into psi 2 z comma 0. This is the Milne-Thomson method, and I have already discussed in previous slide. So where psi 1 z comma 0 is equal to del v del y, and psi 2 of z comma 0 is equal to del v del x. Okay, so here x is equal to z and y is equal to 0. This is the this is actually the so this is the formula of Milne-Thomson method. So here the partial differentiation for the function b with respect to x, this is when y is constant. So del v del x is equal to, so derivative with respect to x of for the function e to the power x is e to the power x, sin y is constant, and it will give phi 2 of x comma y, say. So phi 2 of x comma y is the function. Okay, and it will be e to the power x into sin y. And similarly, del v del y, this is the partial differentiation with respect to y, and it will give e to the power x into derivative of sin y. So derivative of sin y is cos y, and we'll say it is psi 1 of x comma y. Okay, so now putting x is equal to z and y is equal to 0 in the first and second expression, and we'll get e to the power z, first one. So e to the power, okay, in the first expression we'll get 0, that is phi 2 of z comma 0, it will be 0, so sin 0 is equal to 0. And in the second expression, if we put x is equal to z and y is equal to 0, we will get e to the power z into 1, that is e to the power z. Okay, now integrating on both sides, and from we have to find, after integration, f of z is equal to, so integration of e to the power z is equal to e to the power z plus c, where c is an integrating or arbitrary constant. Okay, so next I will take one more example of Milne-Thomson method. So here is the example. If so u minus v is equal to x minus y into x square plus 4xy plus y square, and f of z is equal to, f of z is equal to q of x comma y plus I into v of x comma y is analytic function of z is equal to x plus I y. Then find f of z in terms of z. So here u and v, that means u minus v is given, though both functions are not individually given. Okay, so from this we are looking for either we can find u or we can find v. Then we will apply the Milne-Thomson method, and after applying the Milne-Thomson method we will get the function, analytic function f of z in terms of z. Okay, so let's start with our solution. So here f of z is equal to u of x comma y plus I into v of x comma y is an analytic function. So now, and it satisfies the Cauchy-Riemann equation, so del u del x is equal to del v del y, and del u del y is equal to minus del v del x. So this is the condition of Cauchy-Riemann equations. So if the function is analytic, then it will be satisfied. So that means the Cauchy-Riemann equation is satisfied. So, and also u minus v is given. So u minus v is equal to x minus y into x square plus 4xy plus y square. Okay, so now differentiate this equation. We'll get del u del x minus del v del x, and after differentiation we'll get this x square plus 4xy plus y square, and derivative of x minus y is equal to 1. So similarly, when x minus y is constant, then differentiation of this function is 2x plus 4y. Okay, so now applying, so okay, now applying the Cauchy-Riemann equation, del v del y, del v del x is equal to minus del u del y. So del u del x plus del u del y is equal to this, and similarly we can find the differentiation with respect to y, and from this we'll get this one, del u del y minus del v del x is equal to this. So again we apply the Cauchy-Riemann equation, we'll get del u del y minus del u del x is equal to this. Okay, so from equation 2 and this equation, say this equation number 3, so from these two equations we'll get the value of del u del x and del u del y. So after cancelling the term del u del x from equation 2 and equation 3, we'll get del u del x and del u del y. So here the del u del x is equal to 6xy, and this is equals to say phi 1 of x comma y, and del u del y is equal to phi 2 of x comma y. Same. So now applying the Milne-Thomson method, we'll have f dash z is equal to phi 1 of z comma 0 minus I into phi 2 of z comma 0. So here phi 1 of z comma 0, that means if we put x is equal to z and y is equal to 0, we'll get the value of 0. Similarly, for the second case, if we put x is equal to z and y is equal to 0, we'll get 3z square. So f dash z is equal to 0 minus I into 3z square. Okay, so now integrating on both sides, we'll get f of z is equal to minus 3z to the power 3 by 3. This is actually, there is some mistake here. So it will be actually 3z to the power 3 by 3, that is after cancelling the term 3, we'll get minus I into z to the power 3 plus c, where c is an arbitrary constant. And this is the last problem on lecture 3. Determine the analytic function f of z where b is given. So here b is equal to x to the power 4 minus 6x square y square plus y to the power 4. So from this we are going to find the partial differentiation with respect to x and respect to y. So the partial differentiation with respect to x is equal to this. 4x cube minus 12xy square, and it will be height of x comma y same. And similarly, if we differentiate it with respect to y, and it will give minus 12x square y minus plus 4y to the power 3, and say it will be phi 1 of x comma y. Okay. Now applying the Milne-Thomson method, it will give f dash z is equal to phi 1 z comma 0 plus I into phi 2 z comma 0. Okay, now if we put z comma 0 in the second expression, we'll get the first term is 0 as well as the second term is 0. And similarly, we'll put if we put z is equal to x is equal to z and y is equal to 0 in the first expression, we'll get 4z cube, and the second term is 0 as well. So f dash z, and it will give 0 plus I into 4 z to the power 3, that means 4iz cube. So now integrating on both sides, it will give f of z is equal to iz to the power 4 plus c. So derivative or integration of z2 is equal to z to the power 4 by 4, and 4 is cancelled from numerator and denominator, it will give this. But is an arbitrary constant. I will stop here. Thank you.